We have Dr. Nathan Wiebe, who's joining us today. Nathan is a researcher in quantum computing who focuses on quantum methods for machine learning and simulation of physical systems. His work has provided the first quantum algorithms for deep learning, least squares fitting, quantum simulations using linear combinations of unitaries, quantum Hamiltonian learning, near optimal simulation of time-independent physical systems, efficient Bayesian phase estimation, and also has pioneered the use of particle filters for characterizing quantum devices, as well as many other contributions ranging from the foundations of thermodynamics to adiabatic quantum computing and quantum chemistry simulation. Nathan has received his PhD in 2011 from the University of Calgary, studying quantum computing, before accepting a postdoctoral fellowship at the University of Waterloo, and then finally joining Microsoft Research in 2013. In 2019, he left Microsoft to accept a joint appointment at the University of Washington and the Pacific Northwest National Labs. He currently is a faculty member at the University of Toronto, affiliated with the Department of Computer Science and Physics. And with that, ladies and gentlemen, I'm going to pass it to Nathan.
All right, well, thank you very much. Thanks a lot. So as you can tell, I am incredible about preparing for things. So you'll be seeing my amazing artwork up here the entire time, stick figures and all. But there is one major benefit to my complete lack of preparation for this this talk. And that benefit is that, well, I can talk about anything. So this is my ask from you. In order to make the best of this admittedly kind of crappy situation of me having no good slides for the rest of you, at least compared to the pro slides that John had before this, I want you guys to be loud. I want you to direct this conversation, and if you have any questions, please interrupt me right in the middle of it, because my job is to actually teach you all one thing. Now, I kid you not, actually, this is a challenge that I give to my graduate students. They laugh at me when I tell them this. My challenge to them is every talk I ask that they go to, I ask them to just walk away learning one thing. It doesn't matter what that one thing is, but if you can walk away from every talk you go to having learned something, it's actually amazing how much you end up picking up over a short period of time. So my goal is to help you guys learn that one thing out of this about quantum computing. And please, interrupt me, interact, because that's what I'm here for. So the question, I guess, high level, by the way, does this work? Nope, it does not work. It's not a hot mic. Okay, cool. So I'm going to have to try to do this thingy. Oh, I can. Oh, yeah. Man, I sound like Kool-Aid Man. All right, so basically, the key question that I want to be able to address is, what is quantum computing? Now, I'm grateful to John and perhaps your other speakers that you had beforehand to talk about things like Dirac notation and other stuff. You did talk about Dirac notation, right? Just a little bit. Awesome. So the question is, high level, what and why quantum computing? If nothing else, I feel that's one of the big things to get across, because something that is deeply painful to me is overzealous physicists talking about quantum computing. Now, as a computer scientist, of course, I can look down on all the dirty, unwashed physicists, but from my well-paid and recently renovated research offices, thank you very much. That joke goes over better with computer scientists, it seems. But in any case, the question really deep down is, well, what is quantum computing? How is it similar? And how is it different from ordinary computing? Now, the beginning of all of quantum computing in some ways actually began before quantum computing. The origins of it really can be traced back to the 1970s. And where you got Landauer. Now, Landauer, he was a weird dude in one way. Landauer, he started asking this question: is information physical? Now, what do I mean by that, right? Well, ever since the 1930s, Claude Shannon was able to begin to quantify how much information content there is in a signal. In particular, Shannon ended up showing that if imagine you've got two symbols, 1 and 0, that you're sending across. The amount of information that that ends up being contained in some signal that gets sent across, where there's a probability, say, probability 1 of 1 being sent, and probability 1 minus p of the other one, then the maximum amount of information that can be sent using this channel was given by the Shannon entropy, which is the sum over I pi log pi, with probably a negative sign up there to make it positive. Yeah, that's weird that negative signs make things positive, but for logarithms they do. So this characterizes the amount of information content there is in some signal that goes across. And you can use this to bound any amount of information. But the question is, information, real world, what's the link between the two of them? Well, Landauer ended up showing that if you end up building a computer, which I'm told is something that looks like this. All right. Yeah, I know, right? It's as you can tell, I'm a theoretical computer scientist. But in any case, yeah, you're lucky I didn't try to draw the infinite tape of my Turing machine. But in any case, the idea basically behind this is that normally you think about a computer in isolation, right? It's just a box that's sitting on your desk. But in reality, this box is an actual machine and in contact with its environment. And its environment is at a finite temperature, T, surrounding it. I mean, for something like a dilution refrigerator, which can get down to like 30 millikelvin, that T might be darn near 0. But in reality, it's probably, depending on your machine, if it's like mine, it's probably like 300 or 370 Kelvin with my video card. Yeah, I'm proud of my video card. But in any case, the basic thing is that you've got this temperature. Now, what happens when you do a calculation is that individual bits will periodically get set to 0 or 1. And then they've got to be discarded or reset often in memory. Like, if you do an operation and you've got waste memory that you want to get rid of, you just 0 it. What Landauer realized is that actually there's a minimum energy that it takes taking these qubits out of your computer and discarding them. And that amount of energy is related to the Shannon entropy that a bit can end up holding. And it turns out that every bit of information minimally requires this amount of energy, where K is just some constant. It's known as Boltzmann's constant, that it can be used in order to be able to convert the sort of amount of information that you've got and the temperature into an amount of energy corresponding to it. So this will tell you the minimum cost in terms of energy that it takes to lose a bit of information. So what this ends up saying is that energy and information, they're not separate things. They're actually intimately linked because we need to think about our computers not just as abstractions, but as embodied physical systems that interact with the universe and are limited by the laws of physics. And this raises another question, right? Which I feel is the main reason why I do quantum computing. It's because I want to understand what are the opportunities and what are the limitations that physics plays on our ability to compute. And at another level, what quantum computing ends up allowing, and computer science allows us to do, is to think about the following question, right? I clearly play far too many video games. It's a personal failing that I don't feel too guilty about. But in any case, there's a question about what the computational, if we imagine the universe was a giant video game, kind of, like The Matrix, but hopefully less dark, you can ask yourself, how powerful would that computer need to be in order to be able to do it? Now, Landauer gave some hints that there minimally needs to be a certain amount of energy exchange to do basic calculations. But the question is, what character would a computer need to have in order to be able to describe physics as we understand it? And the answer is astoundingly powerful. I mean, not just like ordinarily powerful. Like, we're talking about, something sensible, right? Like, imagine converting every atom in the planet into a computer and going forward with that. That's sensible. That's something I could imagine us one day doing. Like Elon Musk is probably dreaming it up right now. But quantum is actually vastly worse than that. So to give you an idea, imagine that we had about close to about 100 qubits. Okay? So to be able to describe 100 quantum bits, and you could envision these as like 100 interacting spins in quantum systems. The dimension of the space, or the vectors that we need to be able to describe this, is 2 to the 100. I did a back-of-the-envelope calculation, and at about 2 to the 100, if we could encode 1 bit of information per atom in the Earth, we could actually do this by converting the entire planet over to a supercomputer. Okay? Pretty rad. So, we could the entire planet, if cannibalized, could actually store this amount of information, roughly. Okay, but what happens when we add another quantum bit to it? Well, now, before we've got Earth here, now Mars is going to have to go as well. All right, that's unfortunate, but big deal, right? Well, now we go to 100 and probably about 110 qubits or so. And now we'd have to also consume Jupiter. Once we go to about, and we've got Jupiter, which of course looks like this. Oh, no, I've got colors. You see, this is clearly what they pay me the big bucks for. So now Jupiter's gone. If we go up to about 2 to the 200, then life starts getting a lot worse. Roughly speaking, if you take a look at the total amount of matter in the universe, writing down the wave function that ends up describing these 200 spins would require us to cannibalize the entire universe just to record that information. Okay? So that's what I mean to say that this is utterly frickin' stupid. And it begs the question, well, the universe, Jupiter alone, contains way more than 200 interacting spins. I don't even want to fathom how many interacting spins there are. And the question is, if the universe was a gigantic Turing machine or a giant, RAM computer like we're used to, where does the universe keep its supercomputer? Because the scale of this is enormous, and it seems that the density of computational power that you would need to get the universe to obey its own laws just isn't going to be present. And so the answer, question, please.
Yeah, so what do you mean that to write a wave function for 200 spins, you need to cannibalize the entire universe?
Yeah.
What does that mean?
It's a very good question. I'm not really sure. But this is what I did, basically, with that. What I did is I took estimates on the total number of baryonic particles in the universe, which I believe was on the order of 10 to the 35 or 36. And then figured out, okay, if each one of those could store 1 bit of information, then it gives me a total number of bits. And then I worked out how many bits I would need in order to be able to store that entire vector, assuming that, if we were storing this vector of wave functions, I was actually really optimistic with this. This is like a stupid assumption, but I assumed that we could get by with double precision arithmetic storing each of these numbers. So assuming we only needed 64 bits per element inside this vector of dimension 2 to the 200, the number of bits that we would end up needing when we multiplied 2 to the 200 by 64 was greater than the total number of bits that would be available in the universe. So that's kind of what I was getting at with that. Now, does that mean that this is the ultimate limitation? Of course not. There's better ways that we could encode information than this. But what it ends up saying is that we would have to go to extreme ends to be able to store the information needed to just describe a relatively simple system. Any other questions? Yeah. Yeah. I mean, there's plenty of problems that are incredibly difficult, and plenty of computational models that are kind of physically unrealistic. And the real question, I think, about quantum computing is we want to try to extrapolate out and ask, what's the most powerful computational model that we think is reasonable if we want to describe stuff that's actually in the universe? And so what we want to do is we want to avoid, silly models like this. And also we want to be able to identify what problems are going to be so challenging that even the universe itself might not possess enough computational power to solve. And to me, that's a fascinating question, because it really does go back kind of to this idea that not just information, but computation is physical. And there's ultimate limitations to how much is possible in our universe. Yeah.
What was your estimate again for answer the question, how many qubits does it take to simulate the observable universe?
So for the number of qubits that it takes to do the observable universe, it's about, okay, this is almost an impossible question, because what it ends up meaning, what you've got to ask is what you mean by simulate the observable universe. And how much information content is needed to model the observable universe. So instead, I prefer to focus on more concrete problems. Something like, here's an example. Let's say that, what you've got is you've got a molecule, okay? So this would be an example of methane, okay? So the question is, you could ask questions like, if we want to describe a universe that consists only of this methane molecule, how many qubits would we need in order to be able to adequately model this? Now, surely the universe, if it's got methane in it and is allowing methane to evolve according to the laws of physics, the universe must have at least as much computational power as would be required minimally to solve this problem. And so if you want to take a look at a problem like this, using a minimal basis, the total number of qubits that you would need in order to be able to describe this is you would need 1 qubit for each of the hydrogens, or actually, sorry, you need 2 for each of the hydrogens using a minimal basis. And you need 10 for this one. So for a minimal basis, methane could be described using about 18 quantum bits. Now, this would be 18 per atom. Or not every molecule, of methane in the universe. So we'd have to multiply all these things out, and clearly, right, even in just a mole of methane, we would have an astounding number of qubits that are needed. So to me, though, that's not such a big deal, because theoretical computer scientist, the thing that we care about is we care about the asymptotic scaling. So the reason why 2 to the 200 is really scary to me, but 10 to the 26 is no big deal, is because this is just a constant, whereas this grows exponentially with this n up on top over here. So the thing that if we start taking a look at modeling the world around us as a qubit system, the number of qubits we need just scales linearly with the number of atoms that we need to include in the universe. But if we look at the quantum description that we end up having for large physical systems, the number of bits that we would need to write that down grows exponentially. So it's this qualitative difference between the growth of processing and memory that's needed to be able to describe this that really is what computer scientists care about for this qualitative separation. But again, this is purely qualitative at the moment. To get something a little more quantitative, you'd have to really build like a physical model for how the universe actually computes. And I don't think we're there yet. But qualitatively speaking, people like myself and many others believe that the universe is no more powerful than a giant quantum computer. And so by studying quantum computers, if this belief is true, we shed light on the question of, well, what things are possible, are computable and not computable in the universe. And of course, in the event that the universe can't be simulated by a giant quantum computer, then something really amazing has happened, right? Because to the best of our understanding, quantum theory is fundamental. If the universe computationally is more powerful then quantum mechanics, then there's something going on at a deep level that we don't understand. And we probably would need to revise our understanding of how the universe operates. So from my perspective, it's actually a win-win situation, right? If we can see that we can simulate the entire universe using quantum computing, we've won. And we've found ways of solving all sorts of fascinating problems that we don't know any solutions to at the moment. But if we fail, well, then there's a revolution in physics. So that's what I like thinking of as a win-win situation. But okay, going forward, you know, one of the questions is, what really is quantum computing at a high level? Well, quantum computing, high level, really just does the following. What it does is this is a quantum computer, by the way. You could tell because it's like a dilution refrigerator. I mean, duh, come on, like. Oh, sorry, okay, no, let me make it a proper dilution refrigerator. Here we go. Yeah, so you know when you see all these like fancy pictures of like this like gold thing hanging in the middle of something, and they say it's a quantum computer. Turns out it's not. That's actually the fridge that they put the quantum computer in. But nobody wants to tell you that the fridge looks way cooler than the quantum chip. So, you know, they always take photos of this and claim it's a quantum computer, but it ain't. So anyway, in any case, this crazy like Medusa-looking thing is our quantum computer. And really, what it boils down to is our quantum computer is a device for doing unitary transformations on input state vectors. So the idea basically is that this vector psi that ends up coming in, if this is an n-qubit system, what this boils down to is it gives you a way of storing a 2 to the n dimensional vector inside your quantum computer. The quantum computer, as John alluded to earlier, can end up then carrying out a sequence of gate operations. And these gate operations, they're often drawn, you know, using this diagrammatic notation, something like this, you know. Let's say T, H, this is a totally garbage circuit. But in any case, something like this. And this whole process over here describes a sequence of unitary matrices, so on and so forth. And each of these unitary matrices is going to be a 2 to the n by 2 to the n matrix, okay? And so we can basically, every time we do an operation on a quantum computer, we're multiplying an exponentially big matrix by an exponentially big vector. So that's actually a really powerful thing that we get out of it. So one of the questions to ask is, okay, cool. Quantum computers, like this is perhaps your one thing that, you know, if you walk away with, this would be good. Quantum computers can do unitary matrix vector multiplications on exponentially big matrices. Or sorry, vectors. Okay, and do this at low cost, like polynomial cost in some cases. So that's really kind of cool, but the question is, does the power of quantum computers come from exponentially big matrices? Well, the way I was talking about it, it seems like it does. But actually, that's a damn lie. Everybody who tells you that, you know, quantum computers will get an advantage just because of how big the space is that they're acting on is really kind of doing you a disservice. Because quantum, the advantage that quantum gives, it turns out, does not actually come directly from the size of the vector space, only indirectly. Now, one of the ways that you could see this is, let's see if I planned ahead. Oh gosh, nobody has coins anymore. Let's see if my backpack has a coin. There's always coins in my backpack. Oh, thank you very much. We've got an experimental apparatus here. Wonderful. Thank you very much, John. John, everybody. So, you might ask, with this fancy experimental apparatus, if I flip it, right, this coin over here, it's got two possible states. It's got a 50-50 combination, right, for this. So if I flip it, then there's just two outcomes. How many outcomes would there be if I flip two coins at the same time? Right. How about three coins at the same time? Right. So in general, if I wanted to describe the probability distribution of n coins, the probability distribution requires 2 to the n entries. So quantum and classical are actually more similar than they might seem. You need an exponentially many numbers in order to describe a probability distribution. So if that's true, then everything I tried to sell you on before this is totally bullshit. Because probabilistic algorithms can do actually much of what quantum can do. The question is, what's the difference between what you can do with a classical algorithm and a quantum algorithm if the power doesn't come from the size? And the answer is, well, we don't actually know really where quantum gets all of its power from. It's complicated and it is kind of dependent upon the context that you're looking at. But at a high level, you can kind of envision it as coming from interference between the different possibilities that the probability vector could be in. So to give you an example of this, and unfortunately I'm not going to be able to do the numerics with this pen over here, but trust me on this. So there's this game. I used to unfortunately watch way too much of this lame game show called The Price is Right. And in The Price is Right, they have this game that they call Plinko. Anybody heard of Plinko? Okay. Thank you, thank you, thank you. One person who's definitely skipped too much class to watch game shows. So, Plinko, there's another name for it called a Galton board. Anybody heard of Galton boards? Okay, I see a little bit of nodding your heads. But Galton boards were a 19th century invention. And the basic idea behind a Galton board is the following. What you do is you have a series of pegs that are set up on a board like this. And you drop like a disc. I guess in this country it's called a puck, right? So what happens is you drop the puck down past these defensemen. Yeah, maybe that's an analogy. I don't know. I don't understand sports balls. So what will happen is that this puck will end up getting deflected through this forest of pegs. And small deviations in the position that it ends up falling down into tend to lead to actually big deviations in the random walk that it ends up going through. But it's still a random walk. So what ends up happening in the end is you end up getting a bell curve distribution from this going through. Okay? So this is actually, for The Price is Right, how the game worked is you drop the puck down on the top, and you try to end up, getting it down into the center where you end up getting the highest reward for this. And so if you dropped it pretty much in the center, you would, kind of have the highest probability of getting it with lower returns on investment down towards the tails. Okay? So this is basically how that ends up working. The question is, how would this end up working in a quantum situation? Now, in a quantum situation, there's actually exactly an analog of this known as boson sampling. And the idea behind this is, okay, we're going to do the exact same thing, but we're going to deal with quantum. Now, clearly, the quantum version of this is going to be done with sparkly ink. Because everybody knows quantum is sparkly. I mean, Ant-Man taught me that. All right. So what happens with the quantum version of this is we're going to do the exact same thing. But instead of putting a disk in, now what we're going to do is we're going to put in single photons coming in the top over here. No. Those aren't photony enough. There we go. That's more photony. All right, cool. So these photons are now going to be dropped in the top, right? And can anybody tell me what's one thing that photons can do that pucks can't?
Travel through each other.
They can travel through each other, but importantly, they can interfere with each other. So what ends up happening is that when these particles end up going through, it turns out that the left scattering wave, in some of these cases, will have the opposite sign of the probability amplitude to the right one. And so what will end up happening as this thing ends up going through this network of beam splitters is that they'll end up picking up very different signs or phases in the most general case as it gets to the bottom. And what we end up seeing when it gets to the bottom is actually this weird, chaotic distribution of points at the bottom. And it turns out something really fascinating happens. If you had the ability to even just sample from this probability distribution, it turns out that that would lead to what's called a partial collapse of the polynomial hierarchy, specifically a collapse at the third level. Meaning that basically the polynomial hierarchy is like the relationship between the complexity class P and NP. P is the set of decision problems that can be solved in polynomial time on a Turing machine. The class NP are problems that you can check a solution, and if it's a solution that works, you can easily verify that it works, but it can be really hard to find that solution. For example, winning the lottery is an NP-hard problem. It's pretty easy to be able to determine that you've won the lottery once you've got it, but guessing the right one is really difficult. If any of you disagree with me, then please, I'm willing to share in your winnings. But in any case, well, not that I really need to, because you could probably just guess my password for my banking, and yeah. But any case, this is the idea. You end up getting this kind of interference between things, and the question is, well, what benefits does this have, right? You have this ability to sample from a distribution that's computationally really, really difficult under conventional complexity theoretic assumptions to be able to sample from. So it says that just changing from these classical disks being dropped down the top to quantum disks leads to a radical difference in the computational power of these systems. So, but how does that manifest itself? Well, we can think of a different version of this being a random walk algorithm. So let's consider a random walk algorithm. Yeah, sure. Okay, cool. So I'm not going to have time to actually talk about anything real, but let's go through and talk about the random walk algorithm. Okay. You know what? What the heck? How about I actually do a PowerPoint slide if we don't have that much time?
You can also take questions if you like.
Sure. Yeah. So any questions so far? Yeah.
Is there like any like this way beyond like exponential?
If there's any way to get beyond exponential speedups?
Wait, okay. I heard like there's like algorithms which take way more than exponential time to determine. Have you heard of something called elementary complexity?
No, never.
Okay.
Cool. But there are certainly problems that are undecidable. The halting problem is, of course, one of the fundamental problems that can't be decided on a quantum computer. Yeah.
Did you say the problem was in creating the distribution or sampling from the distribution?
The problem is sampling from the distribution. Creating, in turn, it's the same sort of thing. But if you can show that even if just having a classical computer that could sample from that distribution would have really profound computational implications. Anything else? Yeah, I think this will do.
Excuse me.
Yeah.
So I was wondering, should it be utterly impossible to simulate the universe, given that, let's say we have a 200-qubit system at our hand, and let's say we're trying to simulate a real world where there's another 300-qubit system.
Yeah.
How would you ever simulate that part in a 200 system?
Okay, so this is why I'm saying that, switching from classical computing models to quantum computing models is actually really important, because the number of bits that we end up having in our quantum computer as we grow, we'd like to also be able to simulate a universe with quantum computers in it, if that's the case. And if we needed an exponential growth in this, I agree completely with what you're saying. There's no way that you'd be able to have enough memory in order to be able to describe the system, and so on and so forth. But the nice part is that If you're describing, using a quantum computer, a 100-qubit quantum computer, you only need 100 qubits of memory in order to describe that. So it turns out that because of the fact that the size of the quantum computer in terms of the distribution it can generate scales exponentially with the number of quantum bits, you get around this, this unfortunate problem, and you only need an amount of memory that grows linearly with the size of the system that you're interested in. But let me go through this example, because I want to give you an intuition for how this ends up working before I go. And some of this intuition can be understood by just taking a look at random walks. So the simplest random walk that you can do would be, I go back to John's mystery apparatus here, and I could consider playing the following game. I flip the coin. If it's heads, I move right. And I'll flip it again and drop it because I suck. Oh, tails, I move left. If I continue this over and over again, there'll be a bell curve distribution for my position. And so that's exactly what we expect. Now, if we take a look at the quantum version of this, we could do the exact same thing, but instead of flipping a coin, we're going to flip a quantum coin, which is a Hadamard gate that will create a 50-50 distribution of the bit 0 and bit 1. But because the Hadamard gate has to be unitary, it has to, as a result, map orthogonal input states to orthogonal output states. And that means that you can't just create a 50-50 distribution for both of the inputs. One of them has to have a minus sign in order to make sure this vector for the input on 0 is orthogonal to the output for 1. Okay, so that negative sign means that if I play the same game, if I flip my coin and I get heads, having previously flipped my coin and gotten heads, I'll get a minus sign. But otherwise, I'll just get a factor of 1/2 over here. So what does this lead to? Well, it leads to this situation where if you consider a walker going right, the walker going right will always, in this case, end up getting a positive sign. But if a walker goes left and then ends up going right, in these cases, you can actually end up getting a situation where they get a minus sign because of this transformation at the top. And so this ends up leading to interference between the two. And I did a simple dumb MATLAB calculation to take a look at the difference between this quantum algorithm and the classical algorithm, and something remarkable happens. Note that the classical algorithm, it spreads out like a bell curve the more steps you take. But with a quantum algorithm, what happens is you get two blobs of probability and almost nothing in the middle. And why is that? Well, the reason why this ends up happening is because of interference. The walker reflecting from the right ends up having the opposite signs as the walker reflecting from the left. And those two will cancel out in the middle. And this causes a repulsion effect. And so this means that your walker, instead of following a bell curve, I'll get to you in a sec, will end up actually ballistically getting pushed out to the outside. And this gives you a quadratic speedup relative to random walk algorithms for hitting the edges of graphs and various things like this. So by leveraging interference between the different possibilities that the quantum state could be in, which is exactly what happens here, because some paths will get a positive sign and other paths will get a negative sign depending on the trajectory that they move through the calculation. You can leverage and design interference between the different branches of the problem in order to get effects you couldn't get otherwise. But in the case of probability, probabilities just add. You can't interfere them. So that means the different possibilities of me starting in x0 and getting back to x0, they just add all those possibilities. It's like they don't interact with each other. But in quantum, all the possibilities that the code could be in can interact with each other. And that is the hard game about quantum computing. Actually, you got a question that I forgot about.
What are the different intrinsic factors on a quantum that's related with okay, I'll repeat the question. What are the different intrinsic factors regarding these quantum disks, or sort of the things we're using to model the states of probability that would affect the distribution, and how can we model that knowing it?
Okay, so the kind of intrinsic things that we end up getting are, if I jump back, basically the properties that we end up getting really are the sign distribution. So if we have something that has possible positive and negative signs. If it's all positive, we can just think about it as being no different than a probability distribution, except the sum of the squares is 1. But if we've got negative and positive, then what we can do is we can have situations where what we'll do is we'll begin with 0, we'll split up into 0 plus 1 over root 2, and 0 minus 1 over root 2 by doing a Hadamard. And then by doing another Hadamard and recombining these possibilities back together again, we can cause interference between these possibilities of getting 1 here and minus 1 there. And this leads to interference between the possibilities. So for those of you who have done a little bit of C programming, there's a construct in systems programming known as a fork, where what you can do is you can basically end up getting your code and spawning individual workers in order to be able to kind of execute beyond that point and communicate back. The classical case over here would have all of these independent workers not interacting with each other. Their results would be totally independent. The quantum analog of fork is like this Hadamard gate, and it allows these separate possibilities to now interfere with each other. And the real challenge of quantum computers is to figure out good ways of getting these interference effects to do useful things. Ordinarily, you can end up getting something like this Galton board effect, where the distribution might be incredibly difficult to simulate, but it might be still useless because you can't play Doom on that kind of a machine. And really, that's what we care about, right? So that is the central question. Now, the real sort of thing is, what sorts of quantum computers would we end up needing in order to be able to do important tasks? Unfortunately, because I don't have 2 hours, I can't go through and explain, some of these things. But to give you an idea of the types of things that we can get big speedups for, the biggest things we can get is we can get speedups for simulation. And the best examples that we've gotten for this is chemistry and quantum field theory. Then we have factoring and cryptographic applications. And in these cases, what we can do is we can break RSA and we can break elliptic curve cryptography. But it's worth noting that there's actually other forms of private computing that end up existing in this. So we can do things like blind quantum computing. Bling quantum computing would be really cool. Yeah, definitely sparkly on that one. So blind quantum computing allows you to do a computation in a totally oblivious way that nobody, not even an all-powerful alien, would be able to actually observe without making their presence known. The other things that we can end up doing, these are the biggest exponential speedups, but there's polynomial speedups that are, and I should mention actually recently, topological data analysis under some circumstances also can get an exponential speedup. But polynomial speedups end up existing, and things like search, random walk algorithms, basically any problem in NP, gradient descent, and machine learning. There's many of these problems that end up running, and any problem in NP can be quadratically sped up by using these interference effects. But the real challenge that we've been running into in quantum computing is that it's very difficult to figure out how to profitably use interference in order to be able to solve problems. But fortunately, within the last few years, a handful of techniques have come out that have radically improved our abilities to do this. And these have gotten us to the point where, for the first time, we've been able to take some of these applications and get them within potentially striking distance. And these, to give you an idea about how many qubits we would end up needing, we need about 200 quantum bits, perfect quantum bits, in order to be able to do change the world with chemistry. And we'll need about, for factoring, we need about 2048. Well, actually, we need about 10,000 if we consider all the overheads that end up going in order to do that application. Just to give you an idea, unfortunately, given all the errors that end up existing in realistic quantum devices, we need a lot of redundancy and a lot of error correction. And so considering all the error correction, this goes up to about 100,000 to 1 million physical qubits. And to give you an idea about where we're at right now, IBM could end up making devices that are about on the order of 127 qubits. So with comparable accuracies to what are assumed in those estimates. And so the key point is that we're a long way away from seeing value, at least using existing algorithms for this. But the very fact that we see polynomial rather than exponential scaling suggests that this is in a qualitatively different trajectory than actually any other technology that we've seen so far. And it's my hope that within the next couple of years, as the technology ends up growing, we'll get the ability to not only realize these applications, but entirely new ones that nobody ever dreamed about. After all, the folks fooling around with the Antikythera device back in ancient Greece had no knowledge whatsoever of the possibility of the internet. The possibilities with quantum computing are undoubtedly going to be just as bold going forward. And one of the things that's beautiful about where you're all placed right now is you're all set up to be able to create and discover this whole new future of computing that I'm really excited to have gotten a chance to introduce. Thank you.
Thank you very much, Dr. Nathan Wiebe, again, for the very informative talk. We have very few we're running a little bit over time, but that's fine. If anybody has any questions, we'll be able to take 1 or 2 questions. Yes. Okay.
So I was just having a question about the pegboard. Is there a node at the final outcome? Is there a node right in the center, and is it symmetrical?
Yeah. So, for the quantum case or
The quantum case, yes.
Actually, for the quantum case, if you set it up, it turns out that there's almost no pattern whatsoever, and it's not symmetrical for the random photons being dropped down the top. So it's extremely difficult to predict the distribution. It turns out the distribution is related to a matrix permanent, which is extremely hard computationally to figure out.
And also, is this probability distribution pathological, something akin to the Cauchy distribution?
No, it's not nowhere near that pathological. Actually, in some sense, it's generic. If you take a look at it from the perspective of random matrix theory, it's actually kind of typical of what you would end up seeing with a random circuit or something else like that. So it's really not a pathological distribution in the slightest.
Hello. I like the idea of, GTA 7 to be ultra realistically make the universe, with the laws of physics. Humans are really good at manipulating stuff. How do you think, personally, we can manipulate this quantum bits and recreate the universe with the laws of physics, or maybe with multiverse? I don't like GTA 6 just to have one city and all the others just... I should travel to another universe, maybe in multiverse and all parallel universe. How do you think would it be possible? Thank you very much.
All right, well, sorry, I just have to advertise this because this is one of my great dreams in computing that's actually been achieved. Somebody for the first time managed to run Minecraft inside Minecraft. It was astounding to see the computer that was required in order to do it, and all the redstone, wow. Way cooler than quantum computing. But I got distracted by all the redstone circuitry. What was I talking about? I guess I was probably talking about, the computational power that we end up getting from these sorts of physical systems. I mean, my take on it is that deep down, studying quantum computing does reveal the computational power of some of these particular systems, and also reveals to us, things like interacting photons going through a series of beam splitters. It sounds really stupidly simple, but there's an immense amount of computational power that's hidden there. The real question, though, is how do we leverage that for cool stuff? And, we found a couple of examples of it, but I think we're still on the lookout for new and better things to do. And yeah, I'm lucky that I've had a few good guesses when it came to machine learning and chemistry. But I think there's far more things out there, and I'd like to really understand, what types of quantum computers would be needed in order to really be able to simulate other types and understand really what the practical networking issues we'd have to run into in order to be able to truly build planetary-sized quantum networks rather than the dozens of qubits that we can do at the moment.
Very well. Well, again, thank you very much, Dr. Nathan Wiebe. If you can give a round of applause. Thank you.